Thank you for taking the time to review our work. In this video, we will present our latest research on pairwise point cloud registration, focusing on refining the baseline registration results. This is based on two findings: the limitations of learning-based methods and the advantages of large vision models. In the pairwise point cloud registration task, currently popular deep learning-based methods perform well in terms of matching accuracy and robustness, and they can handle feature alignment in complex scenes. However, they rely on large-scale datasets for training, where data annotation is costly, and their generalization ability is limited by the data distribution, making it difficult to effectively transfer to small sample scenarios. In addition, recent large vision models trained on large-scale image-text datasets have achieved remarkable results in semantic correspondence of images, showing stronger generalization ability across scenes. This provides a powerful pre-trained model for point cloud registration, reducing reliance on paired data. However, how to effectively transfer the general features of vision language models to 3D point cloud registration tasks still faces challenges such as large cross-modal feature space differences, and no mature transfer framework has yet been formed. To address these issues, we propose a novel zero-shot method, RARE, to refine point cloud registration results. Our method leverages correspondences extracted from depth images to enhance point feature representation, thereby eliminating the need for dedicated training datasets. Overall, our contributions are threefold: a training-free zero-shot optimization method, multimodal feature aggregation for registration, and state-of-the-art performance on benchmark datasets. Now, let me explain the problems and solutions behind our method. First, the input of large vision models is often RGB images, while registration methods operate on point cloud data, and there exists a domain gap between them. To address this problem, we adopt an intermediate data form, depth maps, to eliminate this gap. As shown in the figure, to avoid the gap caused by stable diffusion models that are usually trained on RGB data, we use an improved control net trained on depth data as a pre-trained model for point cloud registration. In addition, we project point cloud data into depth maps, further avoiding the gap between images and point cloud data. Second, we found that under the default viewpoint, depth maps obtained by projecting point clouds often yield inaccurate correspondences when using ControlNet. We use a unified view alignment, which enables more accurate correspondences in projected depth maps. Based on the above scheme, we propose a refinement framework, RARE, which leverages diffusion features extracted from depth images to refine registration results. As shown in the left figure, we first use a 3D feature extractor to obtain an initial transformation. Then, using this initial transformation, we project the point clouds into the reference view and the source view, generating two sets of depth images. Next, we employ a pre-trained diffusion model, namely ControlNet as mentioned earlier, to extract diffusion features for each point. After that, through a pixel-to-point feature transfer module, the depth diffusion features and the original 3D features are divided into different groups and fused. To effectively integrate features within different groups, we use an in-layer aggregation module that combines point matching, weighted singular value decomposition, and a transformation selection mechanism to consolidate correspondences. Finally, by analyzing the correspondences between common and uncommon points, this module identifies a set of high-confidence correspondences and computes the final rigid transformation parameters. Overall, the entire pipeline does not require additional data for training, nor does it need specialized training on different datasets, which demonstrates the generalization ability of our method. Finally, let us look at the experimental results. We evaluated RARE on benchmark datasets including 3D Match, 3D Low Match, and Kitty. Overall, across the board, our method consistently achieves state-of-the-art performance, outperforming strong baselines such as VBREdge, SC2 PCR++, and MAC. In addition, we have achieved significant improvements in registration recall rate, rotation error, and translation error across all tested methods on the 3D Match dataset, demonstrating robustness and generalization capabilities. Finally, our ablation study confirms the effectiveness of each proposed component, as removing any of them leads to a decrease in accuracy. In summary, our work has three main contributions. First, we propose a zero-shot approach to refine point cloud registration using depth information, eliminating the need for training on point cloud datasets. Second, we leverage pre-trained diffusion models to extract deep features from depth maps and integrate them with 3D features derived from point clouds through a series of aggregation operations, enabling the establishment of more accurate correspondences. Finally, we conduct extensive experiments on 3 benchmarks and achieve competitive results.